Hello, in this lecture we will find the radius of the small circle. In the drawing we have a square. We know that AB equals to 8 units. So all the sides of square ABCD of course are equal to each other and they are equal to 8 units. And inside square ABCD, this square, we have two circles. The radius of the big circle equals to 2r and the radius of the small circle equals to r, and we want to find out the size of the radius of this small circle of the value of r. Okay, so before we start to solve the question, I will present to you two new rules. Rule number one states that a tangent to a circle is perpendicular to the radius drawn to the point of tangency. So I will read rule number one again. Rule number one states that a tangent to a circle is perpendicular to the radius drawn to the point of tangency. So actually, if we have a circle and we have the center of this circle is at this point O, and we also have tangent to this circle tangent AB is tangent to this circle at this point, we define it as point M. Then if we draw tangent, if we draw radius from the center of the circle that is actually drawn to the point of tangency, that is to say point M. So actually we have this radius, is drawn to the point of tangency, that is to say to point M. Therefore, according to rule number one, the tangent AB is perpendicular to this radius, that is to say this angle is a right angle, it equals to 90 degrees, and this angle is also a right angle that equals to 90 degrees. Okay, so whenever you have radius, like in this drawing, that is drawn to the point of tangency, that is to say point M, then the tangent AB will be perpendicular to this radius, that is to say this angle is 90 degrees and this angle is also 90 degrees. Okay, so I'll repeat again. The rule number one states that a tangent to a circle is perpendicular to the radius drawn to the point of tangency. So whenever the radius of this circle is drawn to the point of tangency, like in this drawing, this radius is drawn to the point of tangency, that is to say point M, then the tangent AB will be perpendicular to this radius, that is to say this angle is 90 degrees and this angle is also equals to 90 degrees. So that is rule number one. So I will present to you also rule number two. Rule number two states that if from one external point two tangents are drawn to a circle, then they have equal lengths. I will read rule number two again. Rule number two states that if from one external point two tangents are drawn to a circle, then they have equal lengths. So actually the meaning of rule number two is that if you have this circle and from external point, that is to say this point P, is an external point in relation to this circle because of the fact that point P is neither inside that circle, neither on the circle, but it is outside this circle, therefore it is considered as external point in relation to this circle, or external point to this circle. And if from point P we draw two tangents to this circle, so this will be the first tangent for this circle. We will define the touching point between this tangent to the circle as point A, and we will draw also second tangent to this circle. We will define the touching point between the second tangent to the circle as point B. So according to rule number two, according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, PA equals to PB. Okay, PA equals to PB according to rule number 2. So whenever you draw from an external point of a circle two tangents to that circle, then the lengths of those two tangents will be equal to each other. That is to say, in this example, PA equals to PB. Okay, so that is actually the meaning of rule number 2. So in the next step, we will define the center of this small circle as point P, and we will define the center of this big circle as point Q, and we will join together points A and B by a straight line. And we will define the touching point between tangent AB to the circle as point M. Again, point M is the touching point between tangent AB and this small circle. Then we will join together points P and M by a straight line. So actually PM is the radius of this small circle, that is to say it equals to R. Why PM is the radius of the small circle? Because of the fact that it starts from the center of the small circle, that is to say point P, and ends at point M, that is a point on the small circle itself. Therefore, line segment PM is the radius of this small circle. And we have rule number 1. Rule number 1 states that if a radius of a circle is drawn to the point of tangency, then the tangent will be perpendicular to this radius. So here we have this radius that is drawn to the point of tangency, that is to say point M is the point of tangency here, and this radius is drawn to the point of tangency M. Then according to rule number 1, the tangent AB is perpendicular to this radius, that is to say this angle is a right angle, it equals to 90 degrees, and this angle is also a right angle that equals to 90 degrees. In the next step, we will define this point as point E, and we will define the touching point between tangent AE to this small circle as point G. Then we will join together points P and G by a straight line. And again, according to rule number 1, so first of all, PG, line segment PG, is the radius of this small circle. It equals to R because line segment GD starts from point G, that is the center of the small circle, and ends at point G, starts from point P, that is the center of this small circle, and ends at point G, that is a point on the circle itself. Therefore, GP or PG is the radius of this circle. And again, we have rule number 1 that says that whenever the radius is drawn to the point of tangency, that is to say point G, then the tangent AE will be perpendicular to this radius, that is to say this angle is equal to 90 degrees and this angle also equals to 90 degrees. Okay? So in the next step we will prove that those two right triangles congruent to each other. So we will prove that the right triangle AMP is perpendicular to the right triangle AGP. I repeat again. We will prove that the right triangle AMP is congruent to the right triangle AGP. Okay, that those two right triangles congruent to each other. First of all, we know that AM equals to AG, AM equals to AG, according to rule number 2. Again, AM equals to AG according to rule number 2. Actually, from the external point A, we have two tangents to this small circle, tangent AM and tangent AG, and according to rule number 2, if from an external point two tangents are drawn to a circle, then the length of those two tangents will be equal to each other. That is to say, AM equals to AG according to rule number 2. And we also know that PM equals to GP equals to the radius of this small circle. PM equals to PG equals to the radius of the small circle. PM equals to PG equals to the radius of the small circle. And the AP is a common side, it belongs to both triangles, so we can write down that AP equals to AP, AP equals to AP. This side is a common side that belongs to both triangles. So AP equals to AP is the common side. So we actually prove that all three sides of the right triangle AMP are corresponding equal to all the three sides of the right triangle AGP. Therefore, we proved that those two triangles can go into each other according to side also. I will write it down. We proved that triangle AMP is congruent. This is the sign of congruent to triangle AGP. According to side rule. So what is side rule? Side rule says that if you have two triangles, if one triangle has three sides that corresponding equal to 3 sides of the other triangle, then those two triangles will be congruent to each other according to side rule. Okay, so from the fact that those two right triangles congruent to each other, we will conclude that those two angles are equal to each other. Those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two angles congruent to each other, therefore those two corresponding angles will be equal to each other. So I'll write it down. Angle PAM, this angle is equal to angle PAG, this angle. Okay, angle PAM equals to angle PAG. And if we define angle PAM as alpha, then angle PAG will be also equal to alpha because of the fact that those two angles are equal to each other. So we found out that angle PAM equals to angle PAG, and according to our definition, both angles are equal to alpha. Okay, so in the next step, we will join together points Q and A by a straight line. And we will define the touching point between tangent AE to this big circle as point N. This point will be defined as point N, and then we will join together points Q and N by a straight line. Actually, line segment QN is the radius of the big circle because of the fact that line segment QN starts from point Q, that is the center of the big circle, and ends at point N, that is a point on the circle itself. Therefore, QN is the radius of this big circle. It equals to 2r, of course. And we have also rule number 1 that says that if a radius is drawn to the point of tangency, like in this drawing, we have this radius Qn that is drawn to the point of tangency, that is to say to point N, then the tangent AE will be perpendicular to that radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule number 1. And we also have the same rule here. First of all, we will define the touching point between tangent DA to the big circle as point L, and point L is the point of tangency, and we have rule number 1 that says that if the radius is drawn to the point of tangency, that is to say point L, then the tangent DA will be perpendicular to that radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay, so in the next step, we will prove that those two right triangles congruent to each other. So actually, we will prove that the right triangle, this right triangle, triangle QAN, is congruent to this right triangle, triangle QAL. We will repeat again. We will prove that the right triangle, triangle QAN, congruent to the right triangle, triangle QAL. First of all, we know that AN equals to AL. AN equals to AN. AN equals to AL according to rule number 2. AN equals to AL according to rule number 2. Actually, we have here external point A, and from external point A we have two tangents to this big circle, tangent AN and tangent AL. So according to rule number 2, if from one external point two tangents are drawn to a circle, then the length of those two tangents will be equal to each other. That is to say, AN equals to AL according to rule number 2. And we also know that QN equals to QL equals to R, that is the radius of this big circle. So QN, this segment line, equals to QR, and both of them are equal to the radius of this big circle, that equals to 2R. Okay, QN equals to QR, and both those two line segments are the radiuses of the big circle, that is 2R. And we also have here a common side that belongs to both triangles. QA is a common side that belongs to both triangles, so we can write down that QA equals to QA is a common side that belongs to both triangles. Again, QA equals to QA is a common side that belongs to both triangles. So we actually proved that three sides of triangle, the right triangle QAN, are corresponding equal to three sides of the right triangle QAL. Therefore, we proved that those two right triangles can go into each other according to side rule. So I write it down. We actually proved that the right triangle QAN, again, the right triangle QAN, congruent, this is the sign of congruent, to the right triangle QAL. QAL according to side rule. Okay, so from the fact that those two right triangles can go into each other, we will conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Okay, so we will conclude that angle QAN, this angle is equal to angle QAL, this angle. Okay, angle QAN equals to angle QAL. And if we define angle QAN as beta, then angle QAL will be also equal to beta because of the fact that those two angles are equal to each other. So we found out that angle QAN equals to angle QAL equals to beta according to our definition. Okay. We will define the touching point between tangent CB to this small circle as point S, and we have here this radius is drawn to the point of tangency, that is to say point S. Therefore the tangent CB will be perpendicular to this radius, that is to say this angle is a right angle, it equals to 90 degrees, and this angle is also right angle that equals to 90 degrees. Okay. And we also know that all four angles of a square are right angles, and especially this angle, angle ABC, it is a right angle, it equals to 90 degrees. Okay, so in the next step we will focus on quadrilateral PSMB. Okay, so we will focus on quadrilateral PSMB. In quadrilateral PSMB, this quadrilateral, we have three right angles. And the sum of three right angles is 90 times 3 is 270 degrees. And we have the rule that states that the sum of the angles in any quadrilateral equals to 360 degrees. That is to say, the sum of these three angles, three right angles, that is 270 degrees, plus the size of this angle that we will define as angle Z, must be equal to 360 degrees. So I will repeat again. According to the rule that I mentioned, if we focus on quadrilateral PSMB, the sum of the angles of the four angles in quadrilateral PSMB must be equal to 360 degrees. That is to say, the sum of three angles, that is 270 degrees, plus the size of the fourth angle that is defined as angle Z, must be equal to 360 degrees. We will subtract from this equality 270 degrees, and we will get that the size of angle Z equals to 360 degrees minus 270 degrees is 90 degrees. So we actually found out that angle Z is a right angle, it equals to 90 degrees. So we write here that angle Z is a right angle So we will continue to focus on quadrilateral PSMB. In quadrilateral PSMB, this small quadrilateral, we have four right angles. And any quadrilateral that has four right angles, it must be at least rectangle, if not square. Okay, so I'll write it down. So because of the fact that quadrilateral PSMB as 4 right angles. Quadrilateral PSMB must be at least rectangle. I will repeat again. Because of the fact that quadrilateral PSMB is 4 right angles, quadrilateral PSMB must be at least rectangle, a rectangle. Okay. And we have the rule that the opposite sides of a rectangle are equal to each other. So in rectangle PSMB, the opposite sides are equal to each other. So PS equals to MB. Side PS for quadrilateral PSMB equals to MB. PS equals to MB. But we know that PS equals to R. PS equals to R. We found out that PS equals to R. PS equals to R. So from this equality we conclude that MB also equal to R. MB equals to R. So here MB equals to R. And according to the rule that the opposite sides of a rectangle are equal to each other, PM will be also equal to SB. PM will be equal to SB. Those two opposite sides in rectangle PSMB will be equal to each other. So PM equals to SB. But we know that PM equals to R. Okay. We know that PM equals to R, so from this equality we will conclude that SB also equals to R. SB also equals to R. SB equals to R, the radius of the small circle. So actually, because of the fact that in rectangle PSMB we have 4 right angles and 4 sides that are equal to each other, it is not a rectangle but a square. Okay? So in the next step we will find out the size of AM. What is the size of AM? From the drawing we can see that the size of line segment AM is actually equals to AB minus MB. Again, AB minus MB equals to AM. AB and AB minus MB equals to AM. Okay, according to the drawing, AM equals to AB minus MB. But AB equals to 8 units. It is given us in the question. AB equals to 8 units. And we found out that MB equals to R. So in total we got that AM equals to 8 minus R. We found out that AM equals to 8 minus R. So I will write here that AM equals to 8 minus R. In the next step we will define the touching point between tangent TC this tangent TC to this big circle as point H. Then we'll join together points Q and H by a straight line. Actually, line segment QH is the radius of this big circle because of the fact that it starts from the center of the circle, that is to say point Q, and ends at point H, that is a point of the circle itself. Therefore QH is the radius of this big circle, that is to say it equals to 2r. And we have also rule number 1 that states that if a radius is drawn to the point of tangency, then the tangent is perpendicular to this radius. So here we have this radius QH, that is drawn to the point of tangency, that is to say to point H. Therefore the tangent TC will be perpendicular to this radius, that is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay, so again we have also the rule that all 4 angles inside the square are right angles, they are equal to 90 degrees, so angle ADC will be equal to 90 degrees because it is one of 4 angles inside square ABCD. Therefore it equals to 90 degrees, it is a right angle. So we will focus on quadrilateral DHLQ. Okay, we will focus on quadrilateral DHLQ. Quadrilateral DHLQ. We have 3 right angles, that the sum of the 3 right angles is 270 degrees. And we know that the sum of the angles in any quadrilateral equals to 360 degrees. And if we define the 4th angle as angle Z, then according to the rule that the sum of the angles in any quadrilateral equals to 360 degrees, that is to say the sum of 3 angles that is equal to 270 degrees plus the size of the 4th angle must be equal to 360 degrees. Okay, so here we will subtract 270 degrees from this equality. We will get that angle Z equals to 360 degrees minus 270 degrees is 90 degrees. So we found out that the size of angle Z is 90 degrees. Angle Z equals to 90 degrees. So this angle is a right angle, it equals to 90 degrees. So, as you can see from the drawing, inside quadrilateral DHLQ, this quadrilateral, we have 4 right angles. Okay, because of the fact that in quadrilateral DNLQ we have 4 right angles, it must be at least a rectangle. So I write it down. Quadrilateral DHLQ must be at least a rectangle. I'll repeat again, because of the fact that quadrilateral DHLQ has 4 right angles, so quadrilateral DHLQ must be at least rectangle. If not a square, it must be at least rectangle. And we know we have the rule that the opposite sides of a rectangle are equal to each other. So that is to say, DA equals to LQ, actually it is DH equals to LQ, those two opposite sides are equal to each other. DH equals to LQ, DH equals to LQ, those two opposite sides are equal to each other, but we know that LQ equals to 2R, LQ equals to 2R, so from this equality we will conclude that DH also equals to 2R, that DH also equals to DH also equals to 2R. Okay, DH equals to 2R. Likewise, DL equals to HQ, because those two opposite sides in rectangle DHLQ are equal to each other, so DL equal to HQ. But we know that HQ equals to 2R. Okay, so from this equality we will conclude that DL also equals to 2R. DL equals to 2R. So DL equals to 2R. So because of the fact that quadrilateral DHLQ has 4 right angles and 4 sides that are equal to each other, actually quadrilateral DHLQ, it is not a rectangle but a square. Okay, if it is a square, it is better, because all the things that you can say about a rectangle, you can say the same things also on a square. Therefore, our conclusions are true, even if quadrilateral DHLQ is a square and not rectangle. Okay? In the next step, we will calculate the size of line segment AL from the drawing. We can say that AL equals to DA over DL. DA minus DL. DA minus DL equals to AL. Again, LA or AL equals to DA minus DL. Again, DA minus DL equals to LA or AL. AL equals to DA minus DL. But what is the value of DA? First of all, DA equals to 8 units. and DL equals to 2R. So we found out that AL equals to 8 minus 2R. So AM equals to 8 minus 2R, and we have already found out that AM equals to 8 minus R. Here AM equals to 8 minus R. So in the next step, actually we know that angle BAD, this angle is a right angle, it equals to 90 degrees because of the fact that it's one out of 4 angles of square ABCD, therefore it is a right angle, it equals to 90 degrees. So we can write down that angle BAD, this angle equals to 90 degrees. Angle BAD equals to 90 degrees. Okay, angle BAD equals to 90 degrees. But we also know that angle BAD, this angle consists of 4 angles, alpha, alpha, beta, and beta. So angle BAD equals to also 2 alpha plus 2 beta. Okay, so from one side angle BAD equals to 90 degrees, and from the other side it equals to 2 alpha plus beta. So we can conclude from this equality that 2 alpha plus 2 beta equals to 90 degrees. That will be equation number 1, that 2 alpha plus 2 beta equals to 90 degrees. Okay, 2 alpha plus 2 beta equals to 90 degrees, so we will divide equation number 1 by 2, and we will get that alpha plus beta equals to 90 degrees over 2 is 45 degrees. So we actually found out that alpha plus beta equals to 45 degrees. But if alpha plus beta equals to 45 degrees, then tangent alpha plus beta will be equal to tangent 45 degrees. I'll write it down. If alpha plus beta equals to 45 degrees, then tangent alpha plus beta will be equal to tangent 45 degrees. And tangent 45 degrees is 1. So we found out, according to equation number 1, that tangent alpha plus beta equals to 1. Again, tangent alpha plus beta equals to 1, according to equation number 1. Tangent alpha plus beta equals to 1. But we have trigonometric identity for the value of tangent alpha plus beta. The following trigonometric identity is that tangent alpha plus beta equals to tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. Okay. Okay, so actually you can substitute tangent alpha plus beta in this equation number 1 by this expression that equals to tangent alpha plus beta, so we'll do it now. And we will get that instead of tangent alpha plus beta, we will write down this expression. We will write down tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. And all this side equals to 1. Okay. In the next step, we will find out the values of tangent alpha and tangent beta from the drawing. So if we focus on the right triangle, triangle APM, in the right triangle, triangle APM, here tangent alpha equals to PM over AM. Okay, tangent alpha equals to PM over AM. I will repeat again. In the right triangle, triangle APM, tangent alpha equals to PM over AM. But PM equals to R. PM equals to R. And AM equals to 8 minus R. So in total we got that tangent alpha equals to R over 8 minus R. So tangent alpha equals to R over 8 minus R. Likewise, we will do the same thing also in order to find out the value of tangent beta. We will focus on the right triangle, triangle ALQ, this right triangle. In the right triangle, triangle ALQ, here tangent beta equals to LQ over LA. Tangent beta equals to LQ over LA. But we know that LQ equals to 2R and LA, so we will find out the value of LA. What is the value of LA? LA, from the drawing we can see that LA equals to DA over LD. DA minus LD. I'll repeat again. This line segment LA equals to DA minus LD. LA equals to DA minus LD, so LA actually equals to DA, that is 8 units, minus LD, that is 2R. So we found out that LA equals to 8 minus 2R. LA equals to 8 minus 2R. Therefore, tangent beta equals to LQ, that is 2R, over LA, that is 8 minus 2R. 8 minus 2R. So in total, we got the tangent beta equals to 2R over 8 minus 2R. Again, tangent beta equals to 2r over 8 minus 2r, and we already found out that tangent alpha equals to r over 8 minus r. Okay, so we found out the values of tangent alpha and tangent beta. So in the next step we will substitute tangent alpha and tangent beta in this equation number 1 by the values that we found for tangent alpha and tangent beta. Okay, so according to equation number 1, we have tangent alpha, and we know that tangent alpha equals to r over 8 minus r plus tangent beta equals to 2r over 8 minus 2r over 1 minus tangent alpha times tangent beta. Okay, so we substitute the tangent alpha and tangent beta by the values that we found for tangent alpha and tangent beta, and we got this equality. So we have here only one variable that is missing, that is the radius of the small circle, and one equation. So it is very simple to solve this equation. First of all, we will find out the common factor for these two expressions, and also a common factor for 1 and this expression. So here we will get that the common factor here is 8 minus r times 8 minus 2r, and in the numerator we have r, and we must multiply r by 8 minus 2r plus 2r, and 2r, we must multiply 2r by 8 minus r. Okay, so actually this expression is exactly equal to this expression, and in the numerator we will substitute 1 by 8 minus r over 8 minus r, that equals to 1, times 8 minus 2r over 8 minus 2r, that also equals to 1. So this expression equals to 1, so we substitute 1 here by this expression that equals to 1, and we must also subtract r times 2r, that is 2r squared. Okay, so actually we have 8 minus r, 8 minus 2r here, and we have 8 minus r, 8 minus 2r here. So when we will move this expression to the numerator, it will be cancelled with the denominator, so we can cancel this expression with this expression because they are equal to each other and they cancel each other. So what is left after we cancel those two expressions is, and all equals to 1 here. So what is left after we cancelled those two expressions? We left with r times 8 minus 2r plus 2r times 8 minus r over 8 minus r times 8 minus 2r minus 2r squared equals to 1. Okay. So that is what is left after we cancel those two expressions. So here we will cross multiply this expression and we will get that r 8 minus 2r plus 2r 8 minus r equals to 8 minus r 8 minus 2r minus 2r squared. Okay, after we cross multiply this expression, we got this expression. We will open the brackets in this expression and we will get that r times 8 is 8r, r times minus 2r is minus 2r squared, 2r times 8 is 16r, 2r minus r is minus 2r squared, all equals to 8 times 8 is 64, 8 times minus 2r is minus 16r, minus r times 8 is minus 8r, minus r times minus 2r is plus 2r squared, minus 2r squared, so plus 2r squared minus 2r squared is 0, so those two expressions will get cancelled, and what is left after we cancelled those two expressions is actually here we have eight r plus 16r is 24r, minus 2r squared is minus 4r squared. It equals to 64 minus 16r minus 8r is minus 24r. So that is what we got. Here we will subtract 24r from this equality. We will get that from equation number 1, and we will get that minus 4r squared equals to minus 48r plus 64. We will add to this to equation number 1 4r squared, and we will get that 4r squared minus 48r plus 64 equals to 0, so we got a quadratic equation. We will divide this quadratic equation by 4 and we will get that r squared minus 12r plus 16 equals to 0. got this quadratic equation, and we know that general formula for a quadratic equation is ax squared plus bx plus c equals to 0, when a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for, and in order to find x, we have a special formula for x. We use the following special formula for x to find out the value of x. X actually equals to minus b plus minus, so root of b squared minus 4 times ac over 2a. Okay, and in our specific quadratic equation, the variable x is r, the radius of the small circle. X equals to r. The coefficients a, b, and c are a equals to 1, b equals to minus 12, and c equals to 16. So we will put this data inside the equation for x, and we will get that x that equals to r equals to minus b equals to minus 12, so minus 12 is 12, plus minus root of b squared, b is minus 12, so minus 12 squared is 144, minus 4 times a times c. 4 times a is 4 times 1 times 16 is minus 64, over 2 times a is 2, so r equals to 12 plus minus 144 minus 64 is 80 over 2. Okay, so we know that 80 equals to 4 times 20, so we'll write it down. 80 equals to 4 times 20. We will get that r equals to 12 plus minus, again 80 is 4 times 20 over 2. So the root of 4 is 2, so we get that r equals to 12 plus minus root of 4 is 2, and inside the square root we have left only with 20, all divided by 2, and we got that r equals to 12 over 2 is 6, 2 over 2 is 1, so r equals to 6 plus minus 20 is 4 times 5, so it is root of 4 times 5, and the root of 4 is 2, so we got that r equals to 6 plus minus 2 times root 5, so we have two answers for r. The first solution that is r equals to 6 plus 2 times root 5, and the second solution is that r equals to 6 minus 2 times root 5. But we know that side AB equals to side AD equals to side DC equals to side BC equals to 8 units. So the size of one side of this square is 8 units. Therefore, and we also know that the small circle is located inside the square, so the radius of this small circle must be less than 8 units. Therefore, actually, the possibility that the radius of the small circle will be equal to 6 plus 2 times root 5, that is actually greater than 8 units, is incorrect answer, because the radius of the small circle must be less than 8 units, because it is inside the square, as you can see from the drawing. So this possibility is incorrect answer, and we left only with the possibility that the radius of the small circle is 6 minus 2 times root 5 units, or in terms of numbers, it equals to 1.53 units. Okay, so we have the radius of this small circle equals to either 6 minus 2 times root 5 units, or in terms of numbers, the radius of this small circle equals to 1.53 units. Okay, so now I will summarize the lecture. Actually, we wanted to find out the radius of this small circle. And we know that one side of square ABCD equals to 8 units. We also know that the radius of this big circle is 2r, and the radius of the small circle is r, and we want to find out the radius of this small circle. That is to say, we want to find out the value of r. Okay, so in order to find out the value of r, I presented to you two new rules. Rule number 1 states that a tangent to a circle is perpendicular to the radius drawn to the point of tangency. Okay, what is the meaning of rule number 1? Rule number 1 states that whenever you have radius that is drawn to the point of tangency, that is to say point M, then the tangent AB will be perpendicular to this radius. That is to say, this angle is 90 degrees and this angle equals to 90 degrees. Okay, so this is rule number 1, and rule number 2 states that if from one external point two tangents are drawn to a circle, then they have equal lengths. So what is the meaning of rule number 2? According to rule number 2, if from the external point P we draw two tangents to this circle, then the length of those two tangents will be equal to each other. That is to say, AP will be equal to PB. So whenever you draw from an external point two tangents to a circle, then the lengths of those two tangents will be equal to each other. That is rule number 2. Okay? Then we actually define the center of this small circle as point P, the center of the big circle is point Q, and we actually proved that those two triangles can go into each other. Why they can go into each other? Because we know that AM equals to AG according to rule number 2, PM equals to GP. They are both the radiuses of the small circle, and AP equals to AP as a common side, so those two triangles can join to each other according to side rule. Therefore, those two angles are equal to each other, and if this angle is alpha, then this angle will be also equal to alpha. Then we prove that those two right triangles are also congruent to each other according to side rule. Why? This side AN equals to side AL according to rule number 2. Side QN equals to side LQ equals to the radius of the big circle, and AQ equals to AQ as a common side that belongs to both triangles. So we prove that those two triangles can go into each other according to side rule. Therefore, those two angles are equal to each other. And this, if this angle is beta, then this angle will be also equal to beta. And then we know that all the sides, all the angles of a square are right angles. So angle BAD equals to 90 degrees. It is a right angle, and angle BAD also equals to, it consists of 4 angles, so it equals also to 2 alpha plus 2 beta. So actually we got that 2 alpha plus 2 beta equals to 90 degrees. We divided the equality by 2, and we got that alpha plus beta equals to 1. Alpha plus beta equals to 45 degrees, and if alpha plus beta equals to 45 degrees, then tangens alpha plus beta will be equal to tangens 45 degrees, and tangens 45 degrees is 1. So we got that tangens alpha plus beta equals to 1, and tangens alpha plus beta equals to 1, and we have a trigonometric identity for the value of tangens alpha plus beta. So in equation number 1, we substituted tangens alpha plus beta by this expression that equals to tangens alpha plus beta according to this trigonometric identity, and we got this equation after we substituted tangens alpha plus beta by this expression. And then we actually substituted tangens alpha and tangens beta by the values that we found out for tangens alpha plus and tangens beta from the drawing. According to the drawing, if we focus on the right triangle APM, tangens alpha equals to r over 8 minus r, and tangens beta equals to 2r over 8 minus 2r. Okay, so we substituted tangens alpha and tangens beta by those two values that I mentioned, and we got this equation after we substituted the values of tangens alpha and tangens beta by the values that I mentioned. We got this equation. We solved this equation, and we got two answers. And the first answer was that tangens alpha, that the radius of the small circle equals to 6 plus 2 times root 5, but it is impossible that it equals to 6 plus 2 times root 5, because one side of square ABCD equals to 8 units, and we know that the small circle is inside the square, so the radius of the small circle must be less than the size of one side of square ABCD, that is actually 8 units. So the radius of the small circle must be less than 8 units, and the answer that the radius equals to 6 plus 2 times root 5 is greater than 6 units. It is impossible, so we left only with the possibility that the radius of the small circle equals to 6 minus 2 times root 5, that is actually about 1.53 units. Okay, so we actually found out that the radius of this small circle equals to either 6 minus 2 times root 5 units, or in terms of numbers, the radius of this small circle equals to 1.53 units. Okay, thank you very much.